This is question 5 from the final exam, and it's worth 18 marks. So this is the biggest and most complicated question in the final exam, and it's AC circuits analysis. So we have this complex circuit where we're given some information and we have to answer a question in 3 parts. Part A, where we're calculating the impedance and phasor representation and so forth. And then in part B, we do a Thevenin equivalent circuit. And then part C depends on part B, where we connect a current source to the Thevenin equivalent, and we're supposed to calculate a voltage. So let's go ahead and start with part A. And what we're going to do is calculate the impedance for Z1. So for Z1, it's a capacitor, and we know the impedance formula for a capacitor, which is Z is equal to 1 over J omega C. Now we've been given the value for the capacitance, and it is 1 millifarad. Okay, so we have 1 millifarad capacitor. Okay, now we need to know omega, and we've been given the frequency. So we know the frequency here is 50 divided by pi hertz. So that's what we have here, and we have to convert that to angular frequency or radiant frequency, and we know that the formula for that is omega is equal to 2 pi f. So we just apply that formula. So we multiply 2 pi by 50 divided by pi, and we get 100 radians per second. And we'll use that later in the overall question, but we're using it right now for calculating the impedance of the capacitor. Okay, so then let's just plug it in to the formula. So Z1 is equal to 1 over J times 100, which is omega, times 0.001, which is the capacitance, and we come up with a value of minus J10 ohms. So that is our first result for part A. So now next we're going to have to calculate the phasor representation of I1. Okay, so the form that the phasor representation is going to take is some magnitude, okay, of the current and some phase. Okay, so how are we going to do this? Well, we've been given the RMS value for I1 here in the question. I1 has an RMS value of 2 amps. Okay, and we're also given the information that I1 leads V1 by 60 degrees. So let's take it one part at a time, okay, and let's deal with the magnitude. So we've been given IRMS is equal to 2 amps, and we know that there's a relationship between the magnitude or peak value of a sinusoid and its RMS value, and it's simply that the peak value or magnitude is the RMS value multiplied by root 2. Okay, so we just apply that to what we know. So it's simply 2 amps multiplied by root 2. So our magnitude is going to be 2 root 2 amps. Okay, so now the next part is going to be to find the phase. So how do we do the phase? So we've been given that the I1 phase leads V1 by 60 degrees. So what does that mean? So that means that the phase of the current is 60 degrees greater than the phase of the voltage. Now, what's the voltage V1? Well, we know the phase of the voltage of V1, it's 90 degrees. Its magnitude is 5, we're not concerned about that right now. We're just dealing with the phase. So we know it's 90 degrees. So all we do is we just plug in the 90 degrees and add it to 60 degrees to get a total phase of 150 degrees for the current. Okay? Because the current is leading the voltage by 60 degrees. Okay? So we put that information together and we bring the magnitude down, right? That's the magnitude. And we bring the phase, and we have the polar representation for the phasor current. So that is our second result for part A. Okay, so now we're supposed to find the time domain expression for I2. Okay, so we're going to do that next. So we're going to find I2 in the time domain. And we've been given the phasor representation of I2. So we're going to have to convert it. So that's a phasor representation, 1 over root 2 at a phase angle of minus 45 degrees. Okay, so how do we convert that to the time domain? Well, it's going to take the form of a magnitude times a cosine at some omega t with some phase angle. So when we're converting from phasor to time domain form, what we do is we drop down the magnitude from the polar form down to a time domain form as a scaling factor for the cosine wave. So we go in both directions, actually. We can go from time domain to phasor, or we can go from phasor to time domain. And then we do the same thing with the phase angle. So that comes here. And we notice that the omega t is not part of this transformation directly. Okay? So, now, we had found omega earlier. We found that it was 100 radians per second when we calculated the impedance Z1. So we already have that result. So we're just going to plug that into the time domain equation into omega as 100t. So again, these numbers are coming in like so, and then this omega, oops, not there. This omega is coming here, and this is coming here. Okay, so that is a time domain representation. So that is the third and final result for part A. Okay, so let's do the Thevenin. Okay, this is worth 10 marks, so it's going to be a big one, the Thevenin equivalent. So now this is a circuit that we have to operate with. We have to find the Thevenin equivalent. And the Thevenin equivalent is going to look like something like this. There's going to be a voltage associated with it. It's going to have some Thevenin voltage, and it's going to have some impedance. So Z Thevenin. Okay? And then it's going to have terminals just like the original circuit. There's going to be a terminal X and a terminal Y. Okay? So both of these are equivalent to each other. So if you can only observe these circuits from X and Y, you won't be able to tell the difference between the two circuits. So now, if you think about making a measurement of the voltage, so let's say you have your voltmeter and you're measuring here, like so, or an oscilloscope, you will get exactly the same measurement if you apply it like so in the equivalent circuit. Okay, so now the other interesting bit about this is that there is no current flowing in the Thevenin circuit if it's not connected to anything. So there's no no current flowing through here. I is equal to 0. So that means the voltage here is going to be the same as the voltage here. So the voltage here is V Thevenin, and the voltage here is going to be V Thevenin. Okay, so that's just a little reminder about the Thevenin equivalent voltage. Okay, so now if you want to find out what the Thevenin impedance is, so that's this guy right here, well then you have to do another step, and that step will be to apply a short circuit. So put a short circuit across both circuits, and then you calculate I. So actually, let's do the phasor form. I short circuit in this configuration, and they should be the same. It's going to be the same. And then you use Ohm's law, right? So you're going to have V Thevenin is going to be equal to Z Thevenin times I short circuit. And then by knowing V Thevenin, which you'll calculate, and by calculating I short circuit, you will be able to calculate Z Thevenin. So that's the theory. So now there's something really good about this circuit though that I think maybe you already spotted, and that is that we do not have any dependent sources. All of these sources are independent. So that means we can use our shortcut method for finding the Thevenin impedance. So we'll get to that later when we're solving, but we're going to use the shortcut method to greatly simplify the problem. Okay, so let's get started with the Thevenin voltage. Okay, so now we need to find the voltage across the terminals here. Okay, and we call that the open circuit voltage, which we know is the Thevenin voltage. So what we notice something really nice about this circuit, and that is at this point here we have a voltage source, and it's defining this voltage with a known value, and that value is 5 at a phase angle of 90 degrees. Okay, so then all we need to do is do a nodal analysis at node A, and then we'll get all the information we need to be able to calculate this V open circuit, or V Thevenin. Okay, so that is the approach we're going to take. So we're going to do nodal analysis, so at node A, and so let us proceed. So look at the branch going over to the left. That's over here, and we have VA minus 5 at a phase angle of 90 degrees, all over an impedance of 5 plus J5. And that, of course, are these components here. Okay? So then, let us continue with our analysis and do the next component, and that is going to be the one going down. And we see that we're opposing the direction of the current source, and so we have a term minus 1 over root 2 at a phase angle of minus 45 degrees, which is the value of I2. And then we have the current going over to the right, and since this is an open circuit, there's no current flowing over to the right. So there's no current, okay? No current, that's 0. So that's why we have 0 here. Okay, So now we have the representation. So now we have to operate with this. So let's go to the next page. Since we're adding these terms, we need to convert to rectangular form. So what I've done here is I have shown, well, not quite that, I've shown this on the complex plane so that I can calculate the rectangular form. For me personally, I like to draw the phasors and the complex impedances on the complex plane, just so that I have a visual about what I'm calculating, and then when I get my results, I want to make sure that they make sense with respect to the diagram. So I'm just showing how to calculate this. We have a phase angle of minus 45 degrees, so that's 45 degrees below the positive real axis, and then we have a magnitude of 1 over root 2, and then we calculate the imaginary component over here, 1 over root 2 times the sine of minus 45 degrees, and that comes up to a value of minus j 1/2. And then we do similar for the real component of the complex number, and that is 1 over root 2 times cos of minus 45 degrees, which gives us 1/2. So we've done the conversion so that 1 over root 2 at a phase angle of minus 45 degrees in rectangular coordinates becomes 1/2 minus j 1/2. Okay. So then, let's bring it down. So what we've done is we've brought this down here, and this minus j5, that's simply 5 at a phase angle of 90 degrees. So that's just a vector pointing up. It's lying on the positive imaginary axis. There's no real component to it, so it's got a magnitude of 5, so that's why we have j5 down here. Okay, so then we have this representation, and then we're going to manipulate to get the phasor form. So then we've just rewritten the last expression on here, and we're just going to manipulate by bringing over this part on the other side, and then we're going to multiply by 5 plus j5 to simplify the expression, and then we go through some steps to come up with VA is equal to 5j5, 5 plus j5. So then what I'm doing is representing that in the complex plane, and then doing the rectangular to polar conversion to get the phasor form. And then our result for the Thevenin voltage is right here. So VA is the Thevenin voltage, and we could have just said V Thevenin. Okay? So then we're going to do the Thevenin resistance of this circuit. So we notice that there are no dependent sources, so we can use the shortcut method. Okay? So when we use a shortcut method, we convert the voltage sources to short circuits, and then we convert the current sources to open circuits. Okay, so what does that look like? Let's redraw this. Okay, now what we've done, we've seen that, okay, there's a current source, and if we zero it, that means 0 amps. So 0 amps are flowing through there. There's no current flowing, so it's effectively out of the circuit, and that's what this represents. So it's out of the circuit. And that applies to the same for the other current source. It's out of the circuit. And then what happens when we have a voltage source? So when we zero a voltage source, it's got 0 volts. So that means on either side there's no voltage difference. And so that appears as a wire. And so that's why we have this representation here as the wire for that voltage source. Okay, so now we have to calculate the equivalent impedance between points X and Y. So what we notice is that this branch out here is not doing anything. There's no current that can flow through here because it's not connected to anything on this side. Okay, so we can safely ignore it. It's gone. So let's just say ignore this guy here. Okay, this branch. And then the current is basically will be able to flow this way. So we just have to calculate the equivalent series resistance of these components here. Okay, so that's pretty straightforward. So then that's simply 5 ohms plus J5 ohms and then minus J5 ohms. So the imaginary bits cancel out and we have just 5 ohms for the equivalent impedance. So it's just a resistor. So now we have all the information we need to make the Thevenin equivalent. In the first step we found the Thevenin voltage, and in the second step we used the shortcut method to find the equivalent impedance, which in this case it's a resistance. Okay, so that's it. So that is the Thevenin equivalent circuit. So that is our answer right there. So then we go on to part C, and that is applying this circuit. We're attaching a current source to the Thevenin equivalent circuit. So let's see what that looks like. So on this side we have the Thevenin circuit, and on this side is the current source that we've attached to it per the question. Okay, and what we're supposed to do is find the phasor voltage Vs, which is across the current source that we've added. So that is the problem that we're trying to solve. So what it looks like to me is that if I can do KVL, do a loop equation, I should be able to solve this fairly easily. But I don't have a voltage for the 5 ohm source, so what I'm going to do is calculate it. So I'm just assigning a reference polarity up here for the voltage through that resistor, and since this is a current source, we know the current that's going to be flowing through that resistor. So then let us come up with the equation. So the voltage phasor through the 5 ohm resistor is simply the resistance times the phasor current flowing through it, and then we plug in the numbers and we get 5 over root 2 at a phase angle of minus 135 degrees. So that's the voltage across the 5 ohm resistor. And then we'll use KVL. We're going counterclockwise around, and so we're going to have our equation minus Vs plus the 5 ohm resistor voltage, and then the Thevenin voltage that we calculated. Okay, and then so now we'll just rearrange the equation and plug in the value for the 5 ohm voltage source, and then we get the equation down here. So now we have to convert this into a form that's more convenient, because we can't add numbers in polar form, so we have to convert it into rectangular form. So now this Thevenin voltage, we've already got the rectangular form from our previous result, so we'll bring that in later. So what I will do is just convert this polar representation to the rectangular form, and I always like drawing in the complex plane just to make it easier, and then doing the analysis, we come up with the rectangular form here, minus 5 over 2 minus j 5 over 2. Okay, then we plug those in to Vs. We continue the same equation, and then we calculate that Vs is equal to 5 divided by 2 plus j 5 divided by 2. So that is our answer in rectangular form, and if we want to convert to polar form, it's 5 over root 2 at a phase angle of 45 degrees.